keyword match or semantic meaning. How do RAG systems actually know the difference? If you've ever wondered how modern AI fetches the absolute perfect piece of information out of millions of documents in a matter of milliseconds, well, you are in the right place. Welcome to this explainer on the inner workings of AI retrieval. Today, we are diving into the evolution of AI search and unlocking RAG retrieval, and we're pulling all of this fantastic insight directly from Colleen KS's RAG Interview Questions Hub over on GitHub, which is just an incredible resource for really understanding how these retrieval systems function behind the scenes. All right, part 1. 2 ways to search. Let's dive right into this. Look, every time you ask an AI a question, it's literally trying to find a needle in a massive digital haystack. And historically, we've had 2 totally opposite ways of doing this. First up, keyword retrieval. You know this one. It's your classic search engine vibe, relying on exact or partial matches. You type fast car, and it looks exclusively for those exact words. It gives you super high precision. But then, on the flip side, we have semantic retrieval. This is where the magic of vector embeddings comes in to understand the actual meaning. It knows that an article talking about a quick automobile is exactly what you want, even if your specific keywords are nowhere to be found. But relying just on keywords, well, that drops you right into what's known as the keyword trap. It's a real problem. Sure, your precision is sky high, but you inevitably miss a massive chunk of semantically related information. Think about it. If a document has the exact answer you need, but uses slightly different phrasing, a keyword search just acts like it doesn't even exist. For developers building out RAG systems, this is a massive, frustrating bottleneck. Which brings us to part 2, the math of meaning. So how exactly do we teach a machine to truly understand context? We use something called cosine similarity. Now, mathematically speaking, this is a metric that measures the angle between vectors. It focuses entirely on their direction, rather than their magnitude or length. When we're dealing with text data and converting words into number vectors, the actual meaning is captured by the direction that vector points in space. Now, what's really interesting here is how you can visualize this. Think of it like this. The angle represents the conceptual meaning, while the magnitude, that just represents the physical length of the text chunk. You could have a super short sentence say, "The dog barked," and then a massive, sprawling paragraph that essentially boils down to "the canine made a loud noise." Because they share that exact same core meaning, their vectors point in the exact same direction. It literally doesn't matter that the paragraph's vector is way longer. And this right here is exactly why cosine similarity is the gold standard for RAG retrieval. Because it's invariant to vector length. It honestly doesn't care if a document is 10 words or 1,000 words long. It gives you these incredibly stable, interpretable similarity scores, so you can retrieve relevant chunks even when text lengths vary wildly. And let's be real, real-world databases are incredibly messy, right? Cosine similarity cuts through that chaos beautifully and improves accuracy across the board. Now, you might be wondering, aren't there other ways to measure this kind of distance? And yeah, there absolutely are. But cosine similarity actively outperforms alternatives like Euclidean distance and the dot product for this specific use case. See, Euclidean distance gets completely thrown off if one chunk of text is longer than another, even if they mean the exact same thing. Cosine similarity just ignores all that noise and stays laser-focused on the actual concept. Okay, let's move along and see how this builds into part 3, the hybrid search solution. So, we've seen the strict, rigid precision of keywords, and we've explored the mathematical power of semantic search. But here's the best part. We don't actually have to choose between them. In a hybrid search architecture, the system is doing a few things. First, it calculates a keyword relevance score. Then, it grabs a semantic similarity score. Finally, it runs both of them through a weighted balanced output. It is basically the ultimate peacemaker. It allows your system to match exact terms, like a highly specific product serial number, while still casting a wide semantic net to catch the broader meaning. So the crucial point to take away here is how these 3 methods stack up. Keyword relies on exact to partial matches for that high precision. Semantic uses vector embeddings to actually understand the concept. And hybrid, it uses a weighted formula to beautifully balance the strengths of both. If you're building a RAG system today, this hybrid approach is absolutely the core architecture you need to deliver the most accurate, reliable answers. All right, wrapping things up with part 4, the engineer toolkit. Because look, knowing how hybrid search works conceptually is one thing, right? But actually implementing it in the real world requires the right tools. back in that very same GitHub repository by Cosine KS that we've been referencing, there is a massive bonus for practitioners. We're talking about a highly curated list of over 120 distinct libraries categorized specifically for data scientists and AI ML engineers. This toolkit is packed with libraries explicitly related to large language models, RAG architectures, and AI agents. Honestly, if you're actively working in this space, heading over to that GitHub repo is just an incredibly practical next step. It is quite literally designed to help you find the exact code bases you need so you aren't stuck reinventing the wheel every time you start a new build. So, what does this all mean for you? It brings us to a final provocative thought. Keyword precision, semantic meaning, or that sweet hybrid balance. How are you going to implement these retrieval methods in your next build? We've unpacked the actual mathematical mechanisms that let modern AI understand and retrieve information. Now, the architectural choices are entirely in your hands. Thank you so much for joining this explainer. Keep learning, keep building, and we will see you in the next one.